Hi guys, you are all welcome to the class again. Today we would like to talk about the different ways we can state the first law of thermodynamics. You know that even from junior high school we have been stating the law of thermodynamics in terms of the law of conservation of matter, and that is very elementary. It's very elementary, and it cannot open up the wide range of meaning of the law of thermodynamics. Therefore, we want to look at the different ways we can state the first law of thermodynamics. So let's take the first way of stating the first law of thermodynamics. Number one, it says that energy, energy can neither be created nor destroyed, but only transferred from one form to another. For instance, if you load a battery, a torchlight with a battery, you know that the battery contains a chemical energy. When you put on the torchlight, the chemical energy in the battery will be converted to light energy. So energy is not lost. Rather, the chemical energy was just converted to light energy. Another instance is when you eat a carbohydrate food. It goes to your body cells inside the organelle known as the mitochondria, and gets broken down into chemical waste, water and carbon dioxide, and energy, adenosine triphosphate. That is a body's energy currency. And through that way, the chemical energy in the carbohydrate has been transferred to another form, which is heat energy. So this is just the first law of thermodynamics. Now let's look at another way we can state the law. Another way we can state the law of thermodynamics is this. The total energy transfer. The total energy transfer. Total energy transfer in any process. You can say in any thermodynamic process is equal to the change in the internal energy of the system. Mathematically, you can say that the change in internal energy is equal to total energy transfer. Total energy transfer in a process. That is another way you can state the law of thermodynamics. Total energy transfer, which means energy can be absorbed by a system, energy can be lost by a system. The total energy transfer gives us the change in the internal energy of the system. You can also state that the total energy transformation of the universe is constant. The total energy transfer or transformation in the universe is constant. The fourth way you can state the first law of thermodynamics is this. The change in internal energy. The change in internal energy of a system is equal to the amount of heat added to the system minus work done by the system, or plus work done to the system. The total internal energy is equal to, that is, the change in internal energy is equal to change in the quantity of heat absorbed minus work done to the system. Sorry, work done by the system. Or change in internal energy equals to change in quantity of heat absorbed plus work done to the system. Work done to the system is positive. Why work done by the system is negative? Negative work. The work done by the system is negative because the system loses energy. The work done to the system is positive because energy is added to the system. So these two are the same, depending on the convention used. Now, you can convert this particular equation. Let's call it equation 1. You can convert it and state it in terms of enthalpy change, where total internal energy equals to change in enthalpy minus work done at constant pressure. But note that work done at constant pressure is P dV, product of pressure times change in volume. This implies that the equation 2 will become total internal change in internal energy equals change in enthalpy minus P dV. Making change in enthalpy the subject of equation 2. Let's call this equation 2. We now write change in internal energy. Before we make it the subject, this is minus P dV. We add change in internal energy equals, okay, we add P dV to both sides of the equation. So change in internal energy plus P dV equals change in enthalpy minus P dV plus P dV. P dV minus P dV will cancel. Then we can now say that change in enthalpy, which is this one, equals change in internal energy plus P dV. This is equation 3.